I'm Sarah Leftwich, and this is my presentation for Lab 5. These were the steps followed in the lab and the relevant physics concepts. First, collect data on the amount of time it takes for a bar magnet to fall through a roll of aluminum foil. Recreate the experiment in a glow script model, modeling the aluminum roll as a stack of conductive rings. Create a function for the rate of change in the magnetic flux through each ring caused by the bar magnet, and use Faraday's law to relate this to the induced current. Use the Biot-Savart law to calculate the force on each ring, and superposition to calculate the force of the whole tube of rings on the falling magnet. According to Newton's third law, this will be equal to the magnitude of the magnet's force on the tube. Calculate the net force on the magnet, then use Newton's second law to update velocity and position parameters in the model to predict the magnet's time spent in the tube. My averaged result for the amount of time the bar magnet spent falling inside the tube was 1.471 seconds, based on timestamps in a video recording of each trial. We can't use a ferrous tube because iron and some of its alloys are ferromagnetic, meaning that orbital and spin motions tend to be aligned in the atoms. So our bar magnet would experience significant magnetic forces near a magnetic tube rather than act as the primary source of magnetic force. While the magnet was inside the tube, its speed decreased dramatically because the downward force of gravity was opposed by an upward magnetic force from the induced current in the tube. When it was above or below the tube, it resumed the normal speed of a falling object. Here's a walkthrough of my glow script functions for this lab. First, I define the parameters of the tube and bar magnet, and then magnetic field of the magnet at relative position R, the change in flux through each ring due to the magnet, the current induced in each ring, the force of the magnet on each ring, the force of the tube on the magnet, the net force on the magnet, and the position and velocity of the magnet. This is a snapshot of how the visual model turned out. At each location in the tube, the direction of the non-Coulomb electric field, and thus the induced current, is determined by the right-hand rule, using the negative rate of change of the magnetic field due to the bar magnet. If we flip the magnet so the south end is on the bottom, the induced currents would change direction. The time spent in the tube was predicted by the model to be 1.221 seconds, which is slightly lower than the experimental value with a percent error of 17%. The accuracy of the bar magnet's dipole moment is crucial to the accuracy of the computational model. The value I used was suggested by my TA and classmates, since my dipole moment calculated in Lab 3 was 6.8, which is very high and probably inaccurate. Using the dipole moment estimate from my peers had a dramatic effect on my results for this model, so knowing the true value for my magnet would make this model highly accurate. We could also try to account for the effects of drag on the falling magnet. Looking at the velocity versus time plot, the velocity is seen to be constant while the magnet is in the tube, so there is no acceleration and thus zero net force on the magnet. This means that the gravitational and magnetic forces acting on the magnet must be exactly equal in magnitude and opposite in direction. What if there was nearly zero resistance in the conductor? Materials with as close to zero resistance as possible are called superconductors, and Faraday's law can still be applied to them. So enough current runs to reverse the increase in magnetic flux imposed so that there will be no net change in magnetic flux, which means a uniform magnetic field and no magnetic force. So the only force acting on the bar magnet would be gravity, and so the magnet would fall normally. What if there were holes or slots cut into the tube? Some of the rings would become open circuits and no current flow would be in those rings, so magnetic force of the tube on the bar magnet is weakened overall. So in conclusion, this was the ultimate intro physics lab because we applied Faraday's law, Biot-Savart law, Newton's second and third laws, the superposition principle, and Ohm's law. My computational model had a 17% error, which isn't too bad since I had to borrow a dipole moment value from PHYS and we didn't account for air resistance. Thanks for a great semester.